Module 10, Lecture B, Pythonic Solutions. By the end of this lecture, you will be able to refactor algorithm implementations to use idiomatic Python constructs without sacrificing clarity or performance, add effective tests and simple benchmarks to validate correctness and performance of algorithmic code, and evaluate and improve the readability and structure of Python algorithm implementations. Pythonic algorithm patterns, safe comprehension patterns. When using comprehensions, aim for clarity and correctness rather than trying to make them as short as possible. They work best as a simple, readable way to filter and transform data in one step, like a small data pipeline. You start with your data, remove what you do not want, and then transform what remains. Each part of the comprehension should be easy to follow, without complicated conditions or hidden side effects that make the logic hard to understand. Use comprehensions mainly for simple transformations and filters, and switch to explicit loops when the logic becomes complex. If a comprehension is filled with nested conditions or changing state, it can become confusing and error-prone, especially in complex tasks like route planning or financial analysis. In those cases, move the detailed logic into separate, well-named functions and let the comprehension act as a clear summary of the overall process. This approach keeps your code more readable, easier to understand, and simpler to test. When working with large datasets, be mindful of performance and memory when using comprehensions. Prefer generator-style patterns that produce values on demand, instead of building full lists when you only need a single pass. Keep your comprehensions and generator expressions simple and focused on one clear transformation step at a time. And avoid long chains of lazy operations that make debugging harder. Finally, check that your approach is efficient and think of comprehensions as clear data transformations rather than just a way to write shorter code. Python code, safe comprehension patterns. Focus on using list comprehensions safely by keeping filtering and transformation steps clear and easy to read. Compare them with explicit loops to judge which approach gives better readability and correctness in a given situation. Understand when it is better to switch from a list comprehension to a generator expression, especially when you want to handle data lazily and safely without creating large intermediate lists. This comment explains that no extra software packages need to be installed because the standard library is enough for the current code. It serves mainly as a note for future developers. If the code is expanded later and new features require additional tools, they could be installed at that point. For now, it simply clarifies that everything needed is already available. We begin with a list of raw temperature readings in Fahrenheit that includes both realistic values and clearly invalid ones. Typical readings might be around 72 or 75.5 degrees, while extreme outliers, such as -999 or 2000, are also present. This mixed list is used to show how we can later filter out unrealistic values and focus only on valid temperature data for further processing. This function checks whether a temperature reading in Fahrenheit falls within a realistic range. It returns true only if the value is between -40 and 212 degrees, including both endpoints. This range is chosen to represent typical environmental temperatures and to filter out extreme or clearly incorrect readings. We define a function called toCelsius that takes one input, a temperature reading in Fahrenheit and converts it to Celsius. Inside this function, we subtract 32 from the Fahrenheit value, multiply the result by 5, and then divide by 9. This calculation correctly and safely transforms the temperature from Fahrenheit to Celsius. We use a list comprehension to clean and convert raw temperature readings in one step. For each Fahrenheit reading, we first call a helper function to check that it falls within a realistic range. If the reading is valid, we then call another helper function to convert it to Celsius. This process produces a new list that contains only valid temperatures, all expressed in Celsius, ready for further use. We begin by creating an empty list that will hold the cleaned Celsius temperature readings. Then, we loop through each value in the raw Fahrenheit data and check whether it is valid using a function that tests if the reading falls within a realistic range. For every reading that passes this check, we convert it to Celsius with a conversion function and add the result to the clean list. This step-by-step loop makes the same transformation as a list comprehension, but in a way that clearly shows each stage of the process. A generator expression lets us process temperature readings efficiently in a single pass. It checks each raw Fahrenheit reading with a validation function and only converts those within a realistic range to Celsius. Because it produces values one at a time instead of storing them all in memory, it is well suited for working with large datasets. This incremental processing reduces memory usage while still filtering and converting the data as needed. We print the results from both the list comprehension and the explicit loop to check that they match. By comparing their outputs, we verify that the transformation and filtering steps are implemented correctly in each method. This confirms that both approaches are equivalent in how they process the data. To find the average Celsius temperature, we first use a generator that goes through each valid Fahrenheit reading and converts it to Celsius as it is processed. We then add up all these Celsius values and divide the total by how many valid readings there are, stored in a separate list. This gives us the average Celsius temperature and shows how a generator lets us safely handle and process data incrementally rather than all at once. This script takes a list of raw temperature readings in Fahrenheit, removes values that are not realistic, and converts the remaining readings to Celsius. It shows 3 ways to do this: a list comprehension, a standard loop, and a generator expression. The list comprehension and the loop produce the same list of Celsius values, confirming they are equivalent for filtering and conversion. The generator expression instead processes each value on the fly without storing all results, which is more memory efficient. Finally, the script prints the Celsius lists and uses the generator to compute the average Celsius temperature, illustrating safe and efficient data handling. Itertools and collections essentials. To write concise and expressive Python code, rely on standard library tools that work with iterables to transform, combine, and summarize data. Instead of using nested loops or manual counters for tasks like counting user appearances or merging event streams, use these built-in modules for clearer and more reliable solutions. When your problem involves combinations, permutations, or aggregations, recognize this pattern and choose the appropriate library feature. This approach keeps your code efficient, easier to understand and less error-prone than custom looping logic. When working with large datasets in Python, iterator-based tools let you process data efficiently without loading everything into memory. They allow you to chain transformations, filter items, and compute results as you go, which suits streaming and multi-stage pipelines, such as cleaning and summarizing data. By relying on these standard library utilities, your code stays clear, high-level, and easier for others to understand, without complex loops or custom iterator logic. Specialized container types in Python provide efficient, ready-made structures for common tasks like counting items, preserving order, and grouping related records. They often perform better and are clearer to read than using basic dictionaries or lists with custom logic. In applications such as recommendation systems, they simplify work like tallying how often items appear together or organizing actions by category. By using these containers, your code more directly reflects the problem you are solving, while performance details such as constant time updates are handled internally by the container instead of scattered throughout your code. Python code, itertools, and collections essentials. This lesson will show how to use the itertools and collections modules in Python to process simple log-style data. You will see how to count items, group related entries, and merge data efficiently using only standard library tools. The focus is on keeping everything beginner-friendly, with clear explanations and comments. If any extra library is needed, you will learn how to install it with a simple pip command. We begin by importing two tools from Python's standard library called itertools and collections, and we focus on the group by and chain features. Group by lets us organize items in a sequence based on a chosen key, which helps categorize data. Chain allows us to link several sequences together into one continuous stream without making extra copies in memory. Using these tools prepares us to process data streams in a flexible and efficient way. We begin by importing two useful tools from the collections module. Counter helps us count how many times each item appears in a sequence, such as tracking how often each user shows up in a list of events. Named tuple lets us define simple data structures with named fields, so we can store and access structured records like events with attributes for user, day, and miles driven in a clear and organized way. We define a simple data structure called an event using the named tuple feature from the collections module with three fields: user, day, and miles. Named tuple lets us quickly create lightweight, class-like structures for storing related pieces of data without writing a full class. It also allows us to access each field using dot notation, which keeps the code clear and easy to read. This approach is especially useful when working with structured data such as logs or records, where every entry follows the same format. We create a list of driving events called Stream1, where each event is stored as a named tuple with fields like user, date, and miles driven. For example, Alice drives 12 miles and Bob drives 7.5 miles, both on January 1st, 2024. Using named tuples gives us a simple, structured way to store this information. This setup acts like a small, sorted log of driving events that we can efficiently process and analyze later. We create another sorted list of driving events to represent extra driving activity, In this list, Alice has an event on January 2nd, 2024, where she drove 5 miles, and Carol has an event on January 1st, 2024, where she drove 3 miles. Each event is stored using an event named tuple, which organizes the information into user, day, and miles-driven fields. This structure makes the data easy to work with and analyze later in the program. We use the itertools chain tool to merge 2 event streams into one continuous sequence without creating new lists. This method is memory efficient because it does not copy the data, it simply links the streams together. The result is a single iterable that we can process as if it were one stream of events. This is especially helpful for large datasets or when we want lazy evaluation, handling each event only when it is needed. We use a counter from the collections module to count how many events each user generates. As we iterate over the combined stream of events, we pull out the user associated with each event. The counter automatically tracks how often each user appears. This gives us a quick summary of the total number of events per user. We begin by printing a header that announces we are showing events per user, which sets the context for the data that follows. Then we display the event counts for each user, summarizing how many events each one has generated. These counts come from a counter object that efficiently tallies how often each user appears in the combined event stream. Presenting this information gives a clear, quick view of user activity and makes it easy to see how many events each user has been involved in. We recreate the merged stream by chaining stream 1 and stream 2 together again, because the previous pass through the merged stream used up its iterator. Once an iterator is exhausted, it cannot be reused for further processing. By creating a new chained stream, we get a fresh iterator that can be safely processed again. This step ensures that any additional operations on the merged data work correctly. We begin by sorting the combined stream of events so they are ordered by day. This step is important because the next phase groups events by their date. The sorting uses a rule that looks at each event's day attribute, ensuring the events are arranged in chronological order. With the events sorted this way, it becomes straightforward to process them in daily batches. We begin by stating that the program will display the miles driven per day to set the context for the output. Then we use a loop to go through the events, which have been grouped by day. This grouping is done with a tool that organizes events based on their day attribute. By processing all events for each day together, we can easily summarize the total miles driven for each day. To find the total miles driven for each day, we use a generator expression that goes through every event recorded for that day and pulls out the miles driven from each one. It then adds these values together to produce a single total for that day. This approach lets us quickly and efficiently summarize how many miles were driven on each day based on the individual events. This line of code prints the day and the total miles driven on that day. It uses a print statement to show the day, the phrase total miles, and the numeric value, followed by the word miles. The result is a clear, readable summary of how many miles were driven each day. The final line of the script prints a confirmation message to the console. indicating that log processing has finished successfully. It signals that all steps have run without errors. This message also confirms that the processing used the itertools and collections modules as intended. Overall, it provides a clear and simple endpoint for the script's execution. This script shows how to use Python's itertools and collections modules to efficiently process log-style data. It defines simple events with a user, a day, and miles driven, then merges two event streams so they can be iterated over lazily without copying. It counts how many events each user has, then recreates the merged stream so it can be used again. The events are sorted by day and grouped to summarize total miles driven per day, and these daily totals are printed. The script ends by confirming that log processing is complete, illustrating how to merge, count, and group data using standard library tools. Pragmatic performance choices. When writing high-level code, the most concise or elegant construct is not always the best choice for performance. You need to balance idiomatic patterns with an understanding of how they behave under real workloads. A technique that works well for hundreds of items may become a bottleneck for millions, especially when large data structures are transformed inside tight loops. In systems with strict latency or completion requirements, this hidden overhead can be critical. Treat performance as a primary design concern and let Python's strengths and limitations guide your choices, rather than relying only on intuition. When optimizing performance, focus on the critical path, meaning the operations that run most frequently or process the most data. In these hotspots, avoid extra layers, unnecessary allocations, or repeatedly creating new collections, and instead favor approaches like streaming values to reduce overhead. In less critical parts of the system, you can prioritize clarity and maintainability with more expressive, higher-level constructs. This balance keeps your design readable while ensuring performance is optimized where it matters most. When optimizing Python code, start by relying on built-in features and standard library tools, since they are usually efficient for tasks like data processing and behavior analysis. If these are not enough to meet your performance needs, then reconsider your overall approach. You may need to break the problem into smaller parts or turn to more specialized libraries. This balance between idiomatic Python style and practical performance helps ensure your code runs effectively in its real environment. Python code, pragmatic performance choices. This segment, we demonstrate practical performance choices using a simple list processing example. We will compare a naive approach that builds full lists in memory with a generator-based streaming approach that processes items on the fly. The focus is on clearly showing timing differences for operations that lie on the critical path of a program. To support these measurements and analysis, you should first install the numerical computing library, NumPy, using the standard package installation command. We use Python's time module to measure how long different functions take to run. This module provides tools for working with time, and here it helps us record the execution time of each approach. By timing the functions, we can accurately compare their performance and see which method of processing data is faster. The function first builds a list of distances in feet, where each distance is 3 times its position in the sequence, starting from 0 up to a given limit. It creates this entire list in memory at once. Then it goes through the list, squares each distance, and adds these squared values together. The function finally returns this total, which represents the sum of all squared distances in feet. This function computes the sum of squared distances using a generator expression to save memory. It takes a limit value, then for each number from 0 up to that limit, it converts the number to a distance in feet by multiplying by 3, squares that distance, and adds it to a running total. Because it uses a generator, it processes each value one at a time instead of creating a full list in memory. This approach is more efficient and scales better for large datasets with many distance calculations. The measure time function is used to find out how long another function takes to run. It first records the current time using a precise performance timer, then calls the target function with a given limit and stores its result. After the function finishes, it records the time again and computes how much time has passed. It finally returns both the function's result and the measured duration, so you can see the output and how long the computation took. We define 2 different workload sizes to test performance. The small limit is set to 10,000 items, representing a manageable dataset for basic performance checks. The large limit is set to 2 million items, representing a much heavier workload. Using these 2 sizes lets us compare how efficiently and quickly different approaches handle smaller versus larger amounts of data. We begin by timing the list-based method on a small workload. A timing function runs the sum of squares list function with a small limit and records how long it takes to finish. It also captures the result of the computation and the elapsed time. These values are stored so we can later compare both the output and performance of this list-based approach with other methods for processing lists. To evaluate the generator-based approach on a small workload, we use a timing function that runs the generator with a small limit. This timing function returns both the generator's output and how long it took to produce that output. We save these 2 values so we can later compare the generator's performance and analyze its execution time. To evaluate the performance of the list-based approach on a large workload, we run the sum of squares function that uses a list comprehension with a large limit. This function first builds a complete list of distances in feet, then computes the sum of their squares. We use a timing helper to record when this computation starts and ends, allowing us to calculate how long it takes. Both the computed sum and the elapsed time are saved for later comparison with other approaches. To measure the performance of the generator-based approach on a large workload, we use a timing function that takes the generator and the large limit as inputs. This timing function records the start time with a high-resolution performance counter, then runs the generator, which computes the sum of squares of distances in feet without creating a full list in memory. After the generator finishes, the function records the end time, computes the elapsed time, and stores both the sum and the execution time for later analysis. We print a summary of the results for the small workload to verify that both approaches match. By comparing the outputs from the list-based method and the generator-based method, we can confirm that they produce the same results. This check ensures that both implementations are correct and behave consistently. This line prints a summary to verify that the list-based approach and the generator-based approach give the same result for a large workload. It directly compares the numerical outputs from both methods and reports whether they match. This check is important because it confirms that any performance comparison between the two approaches is based on correct and equivalent results. This line measures how long the list-based approach takes to run for a small workload and then prints that time. It uses a rounding function to limit the result to 6 decimal places, so the number is neat and readable. This formatting makes it easier to clearly compare the performance of this method with other approaches. This code measures how long the generator-based method takes to handle a small task and then prints that time. It rounds the elapsed time to 6 decimal places, so the result is neat and easy to read. This precise timing output makes it straightforward to compare the efficiency of the generator approach with other methods. This line reports how long the list-based approach takes to handle a large workload. It uses a rounding function to format the measured time to 6 decimal places, making the result easier to read. By providing a precise execution time, it allows you to clearly compare the performance of this method with other approaches. This line reports how long the generator-based approach takes to handle a large workload. It formats the measured time by rounding it to 6 decimal places, so the result is easy to read. This makes it straightforward to compare the generator method with the list-based method and see which one is more efficient for large data sizes. The code compares how long 2 approaches take to handle a large workload, one based on a list and the other on a generator. It measures the execution time of each method and then checks which one is faster. If the list-based method finishes sooner, it prints that the list is faster. Otherwise, it reports the generator as faster. This gives a clear result about which approach performs better for heavy computation. This script compares 2 ways to sum the squares of distances in feet, one using a list that stores all values in memory, and one using a generator that produces values on the fly. It measures how long each method takes for both small and large workloads. For small workloads, the list version can be slightly faster because it is simpler. For large workloads, the generator usually wins because it avoids the memory cost of building a full list. The script also checks that both methods give the same numerical result, while showing that the generator is typically more efficient at scale. Testing and timing. PyTest for algorithms. When working with algorithmic code, using a lightweight testing framework like PyTest helps you write small, focused tests that check how each function behaves. You verify what inputs it accepts, what outputs it produces, and how it handles edge cases. For example, a shortest path algorithm should be tested to ensure it finds correct paths, deals properly with disconnected nodes, and responds safely to invalid inputs such as unsupported negative weights. Clear tests like these create a safety net, so you can refactor or optimize your algorithms with confidence, knowing that unintended changes will be caught quickly. PyTest is especially useful for algorithmic tasks because it supports parameterized tests, which let you define a set of related inputs and expected results, and then run the same test logic on all of them. This means you do not need separate tests for each case, such as sorted, reverse sorted, or random data for a sorting or searching algorithm. By grouping these scenarios together, you keep your tests concise while still checking that the algorithm behaves correctly across many input types. This makes it easier to validate algorithms on diverse real-world data, such as transaction logs or sensor readings. PyTest helps you go beyond checking basic correctness by testing how algorithms behave under stress and unusual conditions. You can write tests that confirm not only correct results, but also that failures, such as non-convergence or hitting resource limits, are handled properly. This kind of defensive testing is especially important in areas like logistics and finance, where data can be messy. PyTest also works well with coverage and timing tools, so your test suite can cover both normal and edge cases and act as a living specification that guides safe changes to your algorithms over time. Python code, PyTest for algorithms. This material shows how to write simple tests in a pytest style for basic algorithmic functions. It explains how to use parameterized style checks without relying on an external pytest installation. You also learn how to run these tests manually and report clear pass or fail messages. Overall, the focus is on lightweight, readable testing that you can execute and interpret on your own. In real software projects, you would normally use the PyTest library to manage and run your tests efficiently. Installing and using PyTest is the standard practice in production environments. In this script, however, we are intentionally using a simple manual testing approach instead. This lets us demonstrate testing concepts without relying on any external tools or dependencies. This function converts a temperature from Fahrenheit to Celsius using a standard formula. It takes one input, the temperature in Fahrenheit, subtracts 32, multiplies the result by 5, and then divides by 9. These steps change the value from the Fahrenheit scale to the Celsius scale. The function then returns the temperature expressed in degrees Celsius. This function finds the maximum subarray sum in a list of numbers by tracking two running values. It starts by setting both the current best sum and the overall best sum to the first number. As it moves through the list, it updates the current best sum by choosing whichever is larger, the current number alone or the current number plus the previous current best. It then updates the overall best sum if this new current best is larger. At the end, it returns the overall best sum, which is the maximum subarray sum. This function acts like a simple version of PyTest assertions. It takes the value your code produced, the value you expected, and a label describing the test. It compares the received and expected values, and if they match, it prints a pass message with the label and the value. If they do not match, it prints a fail message that includes the label, the received value, and the expected value. This provides a basic way to check whether your function outputs are correct without using an external testing library. we define a test function to check the Fahrenheit to Celsius conversion. Inside it, we create several test cases, each with a Fahrenheit input and its expected Celsius output. For each case, we generate a short description of what is being tested, run the conversion on the Fahrenheit value, and round the result to 2 decimal places. We then use a helper function to compare this calculated Celsius value with the expected one, using the description for context. This process confirms that the conversion function works correctly across multiple different inputs. We use a parameterized test function to verify the maximum subarray sum algorithm. A list of test cases is prepared, where each case includes an input array and its expected maximum subarray sum. For each case, we extract the array and expected result, then generate a short description of what is being tested. We run the maximum subarray sum function on the array, compare the output to the expected value with a helper function, and report whether the test passes or fails based on that comparison. The code first checks whether it is being run as the main program, so that the test logic only runs when the script is executed directly. It then calls a test for the Fahrenheit to Celsius conversion function, which verifies that the conversion works correctly for several inputs. After that, it runs a test for the maximum subarray sum function to confirm it produces the correct results for different arrays. When all tests pass, the program prints a message indicating that all algorithmic tests finished successfully. This script uses a simple pytest-like style to manually test 2 algorithmic functions without relying on external libraries. One function converts temperatures from Fahrenheit to Celsius, and the other computes the maximum sum of any contiguous subarray. Helper checks compare each function's output to expected values and print pass or fail messages. The tests include typical cases, such as converting 32 degrees Fahrenheit to 0 degrees Celsius, and finding a maximum subarray sum of 7 for a specific sequence of numbers. After running all tests, the script reports that testing is complete, offering a straightforward way to verify that the algorithms work correctly without using the full PyTest framework. Timing with timeit. To measure how fast your Python code really runs, simple tools like a wall clock or print statements are not reliable. Instead, you can use the timeit module, which runs a small piece of code many times and reports how long it takes. This repeated execution reduces random noise from the system and interpreter, giving more stable results. You typically apply timeit to a specific task under controlled conditions, so you can consistently compare different implementations and see which one is faster for your particular inputs. The timeit module is most useful when you carefully choose what to measure so it reflects real work. For example, if you build a recommendation system, you should time the ranking function using realistic input sizes. And for scientific code, you should use arrays similar to your real data. Running timeit multiple times helps average out random variation and reveal true performance. You should also separate one-time setup from the core operation so you measure the actual cost of the algorithm itself. When you use timing tools, the goal is to interpret the results so they inform your design decisions. Sometimes a clearer, more readable implementation that is only slightly slower is an acceptable trade-off. However, If a small change leads to a large performance gain, that is a strong reason to optimize. Over time, you can create benchmarks for your important algorithms and run them with each major update. This helps you track performance, detect slowdowns early, and keep a good balance between speed, clarity, and maintainability. Python code, timing with timeit. Use the timeit module from the standard library to measure how long small algorithms take to run. For example, you can compare the performance of a loop-based approach to computing a sum with the performance of the built-in sum function. Running each option many times helps smooth out random variation and reduces measurement noise. This repeated timing gives more stable and reliable results, making performance differences clearer. In this part of the code, we only use modules that come with Python's standard library, so there is no need to run any pip install commands. Everything required for the script is already included with a normal Python installation. This means you can run the code without installing any extra packages. It simplifies setup and avoids dependency issues. We use the timeit module from Python's standard library to measure how long small pieces of code take to run. This tool is designed for timing code execution accurately by running the same snippet many times and averaging the results. It is especially helpful when we want to compare the performance of different ways of implementing the same task. We define a function that takes a list of numbers and computes their sum using a simple loop. Inside the function, we start a running total at 0, then go through each number in the list and add it to this total. After all numbers have been processed, the function returns the final total, which is the sum of the list. This method is clear. This function quickly adds up all the numbers in a list by using Python's built-in sum capability. Instead of manually looping through each element and adding them one by one, it relies on an internal implementation that is already optimized. As a result, it computes the total more efficiently and is generally faster than writing the addition process yourself. We begin by creating a list of numbers from 1 to 50,000 to act as a realistic dataset, such as distances in miles. This list gives us a large, consistent, and predictable set of integers. We then use it to test and compare how efficiently different summing functions perform. Using a simple numeric range makes it easy to generate the data and focus on timing the functions accurately. We use a timer from the timeit module to measure how long the slow sum function takes to run. The timer is configured with a statement that calls slow sum on the numbers list. Its setup step imports both slow sum and the numbers list from the main script, so they are available when timing begins. This arrangement lets us run slow sum repeatedly under the same conditions and accurately evaluate its performance. We create a timer object specifically to measure how long the fast sum function takes to run on a prepared list of numbers. The code being timed is simply the fast sum applied to that list. In the setup phase, we import both the fast sum function and the numbers list from the main module. This setup ensures the timer has everything it needs to run the function and record its execution time accurately. To measure how long the slow sum function takes to run, we use the repeat feature of the time measurement tool. which runs the function many times and records several timing results. In this case, we perform 5 repetitions, and each repetition runs the function 10 times. We then look at all the recorded times and take the smallest one. Using the minimum time helps reduce the effect of random slowdowns and gives a more stable and reliable estimate of the function's best execution time. We use the time measurement tool to see how quickly the fast sum function runs. The repeat method runs this function several times in groups, which helps smooth out random fluctuations in timing. From these repeated measurements, we then take the minimum time as the best observed performance. This process gives a more stable and reliable estimate of how fast the fast sum function actually is. We report the best execution time of the slow, loop-based summation function, measured across 10 runs. The result is rounded to 6 decimal places and given in seconds. This single value lets us clearly compare the performance of the loop-based approach with other summation methods. We report the best execution time of the fast sum function, measured across 10 runs, and round this value to 6 decimal places for clarity. This timing is then compared with the slower sum implementation. The goal is to clearly show the performance difference between using Python's built-in sum function and a manual loop-based approach. To measure how much faster the fast sum function is than the slow sum, we compute a speedup factor. We do this by dividing the best recorded time of the slow sum by the best recorded time of the fast sum. If the fast sum time is greater than 0, we perform this division. If it is 0, we treat the speedup as infinite. We then report the speedup, rounded to 2 decimal places, to show how many times faster the fast sum ran compared to the slow sum. This script uses the time measurement module in Python to compare 2 ways of summing a list of numbers. One function adds the numbers using a manual loop, while the other uses the built-in sum function. By timing each approach over many runs, the script finds the best execution time for both. It then computes how many times faster the built-in version is, showing that the built-in sum is usually much more efficient than a loop for this task. Catching performance regressions. Catching performance regressions helps keep your algorithms efficient as the code evolves. Even when tests pass, small changes in data structures or control flow can introduce serious slowdowns, especially with large datasets. To avoid relying on user complaints, you should continuously test performance and treat it like any other part of your test suite. This means turning one-off timing experiments into repeatable checks that run alongside your functional tests, so you detect and fix slowdowns early in development. To avoid performance regressions, create simple benchmarks for your key algorithms and measure how long they take to run on realistic input sizes in a controlled environment. Use these measurements as a baseline and record them. After any code change, run the same benchmarks again and compare the new times to the baseline. If the runtime increases significantly, it signals a potential performance regression, even if the algorithm still produces correct results. Make performance checks a routine part of your testing process, so they become a core quality measure. For small projects, you can run benchmarks manually before major changes and record the results to watch for trends. For larger systems, automate benchmarks and continuous integration. compare them with past results, and flag any significant slowdowns, such as increased search latency or longer report generation times. This helps you catch performance regressions early, find their causes, and optimize or redesign the system before users experience noticeable slowdowns. Python code, catching performance regressions. Set up simple timing baselines to detect when algorithm performance gets worse over time. Use consistent, repeatable timing measurements to compare the original implementation with any refactored version. Monitor these results and issue a warning whenever the new version becomes noticeably slower than the established baseline. This line indicates that you should install 3 Python libraries: pytest benchmark, matplotlib, and seaborn. Pytest benchmark is used to measure how fast your code runs so you can detect performance regressions. Matplotlib and seaborn are visualization tools that let you create plots and graphs. Together, they help you both benchmark your code and clearly analyze the performance results. We begin by importing a few key tools from the Python standard library to support performance analysis. The timeit module lets us measure how long small pieces of code take to run, which is useful for comparing algorithms. The statistics module provides functions such as the mean and standard deviation to summarize and interpret these timing results. The math module is also imported, not for immediate use, but to allow for possible mathematical operations or extensions later on. This function, called original sum squares, computes the sum of all squared numbers from 0 up to a given limit. It begins by setting a running total to 0, then uses a loop to go through each number from 0 up to, but not including, the limit. For each number, it adds that number squared to the running total. After the loop finishes, it returns the final total, which is the sum of these squares. This refactored function computes the sum of squares from 0 up to a given limit. It first uses a list comprehension to generate the square of each number in that range. Then it applies Python's built-in sum function to add all those squared values together. This design makes the code more concise and can be more efficient than using a traditional loop. This description explains a function that measures the average runtime of another function for given arguments. It uses a timing tool to repeatedly run the target function with a specified limit value, by default running it several times. The timing tool returns a list of how long each run took. The function then uses a statistics utility to compute the mean of these times, producing a single average runtime value as the final result. To establish a timing baseline, we first choose a representative input size, here set to 200,000. We then measure how long the original version of the algorithm takes to run on this input. This is done by using a function that computes the average runtime for the original algorithm with the chosen input size. The resulting value, called the baseline seconds, represents the typical execution time of the original algorithm for that input, and will be used for comparison with other versions. We measure the execution time of the refactored function using the same input size as the original, to ensure a fair comparison. A timing helper function is called with the refactored function and the baseline limit, and it runs the refactored code multiple times to compute an average runtime. The resulting value stored as the refactored seconds represents the average time the refactored function takes to complete for that input size. We set a threshold of 25% slowdown to flag any serious performance regressions. To measure slowdown, we subtract the baseline execution time from the refactored execution time. Divide that result by the baseline time, and then multiply by 100 to express it as a percentage. This percentage tells us how much slower the refactored version is compared to the original, and whether it exceeds our acceptable limit. The code prints a concise summary of how long each version of the algorithm takes to run. It reports the baseline time for the original algorithm and the time for the refactored version. Both values are rounded to 6 decimal places to keep the comparison clear. This makes it easy to directly compare the performance of the two implementations. The code compares the slowdown percentage to a predefined threshold to decide if performance is acceptable. If the slowdown is higher than this threshold, it reports a regression and states how much slower the refactored version is than the baseline. If the slowdown stays within the threshold, it reports that the performance change is acceptable and shows the percentage difference from the baseline. This script checks for performance regressions by comparing how long two versions of a sum of squares algorithm take to run. One version uses a simple loop and serves as the baseline, while the other uses list comprehension and is measured against it. Both are timed with the timeit module over multiple runs to get average runtimes. If the refactored version is more than 25% slower than the baseline, the script issues a warning. Otherwise, it reports that the performance change is acceptable. When you run it, you see the baseline and refactored timings, along with a clear message about whether a regression was detected. Readable algorithm structure. Clear names in code. Using clear, descriptive names in your code is essential for readability and long-term maintenance. When someone examines a search routine or data transformation pipeline, they should be able to understand what is happening just by reading the function and variable names. These names should describe the purpose of each part, such as indicating whether a value is a candidate solution or a priority queue, instead of focusing on low-level details. This practice becomes especially important in complex domains like finance or logistics, where clear naming helps guide readers through intricate algorithms. When naming functions in algorithmic code, focus on the decision or outcome they produce, not the internal steps or data structures they use. Inside the function, choose variable names that clearly match the main conceptual actions, such as filtering or sorting. Use the same terms for the same concepts throughout the codebase, so the overall algorithm is easier to follow. Avoid mixing different names for the same idea, because inconsistent naming makes the logic harder to understand. When you name elements in your code, choose labels that will make sense to future readers, including yourself under stress. Avoid vague names that say nothing about what the value represents, and instead use names that clearly express purpose and any important constraints. Distinguishing things like raw sensor readings from calibrated measurements and including units, such as duration in seconds, helps prevent subtle bugs. By treating naming as a core part of design, you make your code more self-explanatory, easier to debug, and simpler to maintain and extend. Python code, clear names in code. This lesson shows how clear, descriptive variable names make algorithms easier to read and understand. It compares a simple distance filtering task written with confusing, vague names to the same task written with meaningful, descriptive names. Both versions produce identical results, but the clearer names make it much easier to follow the logic and purpose of each step. By printing and comparing the outputs, you can see that readability improves without changing the algorithm's behavior. This line is simply a placeholder comment explaining that the script does not require any extra installations. It jokingly mentions a fake package to highlight that the code uses only standard Python libraries. The main point is that the script is easy to run and fully compatible without needing additional dependencies. This example describes a poorly named function that filters a list based on a threshold. The function takes a list of values and a threshold number, then creates an empty list to store results. It goes through each value in the input list and checks whether it is less than or equal to the threshold. If the value meets this condition, it is added to the results list. In the end, the function returns this list of all values that pass the threshold test. We define a function that filters trip distances based on a maximum allowed mileage. It takes a list of trip distances and a maximum distance as inputs, then creates an empty list to store the qualifying trips. The function goes through each trip distance, and if a trip is less than or equal to the maximum allowed miles, it adds that distance to the results list. After checking all trips, the function returns the list of trips that do not exceed the specified maximum distance. We begin with a list of trip distances in miles, represented as floating point numbers for different trip lengths. This list serves as the common input to both functions we want to compare. Each function uses the same distances to decide which trips are short, based on a predefined cutoff value. This setup lets us see how each function filters out short trips from the overall list. We set a value of 5 miles as the maximum distance for a short trip. This value acts as a threshold that defines what counts as a short trip. Using this limit, the code can filter out any trips that are longer than 5 miles. Only trips at or below this distance are included in the final results. We use a deliberately poorly named function called the bad filter to process a list of trip distances and a maximum allowed mileage. This function returns only the trips that are less than or equal to the given maximum distance. Its main purpose is to provide a comparison point, showing that the same logic can be written with either clear or confusing names. This highlights how naming choices strongly affect code readability, even when the underlying behavior is identical. We use a clearly named function called filter short trips that takes 2 inputs, a list of trip distances in miles and a maximum distance that defines what counts as a short trip. The function removes any trips that are longer than this maximum and returns only the ones that meet the short trip limit. Using descriptive names makes the function's purpose and logic easy to understand, which improves readability and helps others quickly see what the code is doing. The code prints the output of a function that uses unclear variable names, showing which distances were selected as short trips. This confirms that even with confusing naming, the function still returns the correct filtered results. The print statement labels this output as bad names result miles to make it easy to compare with the version of the function that uses clearer names. This example shows the output of a function that uses clear, descriptive variable names. The key idea is that meaningful names make the code easier to understand and read. Even though the logic is identical to a version with vague names, a well-named version is much more understandable. This highlights how naming alone can greatly improve code readability without changing what the code actually does. This script shows why clear variable names matter in Python. It compares two functions that both filter a list of trip distances to keep only those shorter than 5 miles. Although the functions produce the same correct result, one uses vague names and the other uses descriptive names. The example demonstrates that meaningful names do not change what the code does, but they make it much easier to read, understand, and maintain. Modular algorithm design. When designing algorithms, break complex problems into smaller tasks, each with a clear purpose. Look for natural points in the workflow where you can create separate functions or methods, such as loading, cleaning, transforming, and summarizing data in a pipeline. This modular structure makes the overall algorithm easier to understand because you can follow the main flow through a few function calls and examine details only when needed. It also turns your solution into a set of reusable components, which improves readability and maintainability. Modular algorithm design lets you describe an algorithm at different levels of detail without overwhelming the reader. At a high level, you can show the main purpose using simple function calls that read like clear sentences. When more detail is needed, each function, such as reading input data or applying business rules, can be examined on its own. This way, the reader can focus on one part at a time instead of getting lost in the full complexity of the algorithm. Modular design breaks an algorithm into separate functions with clear inputs and outputs, which makes the code easier to test, reuse, and evolve. Each part can be tested on its own, helping you find bugs early. These independent pieces can then be reused in other algorithms, reducing duplication and keeping the codebase cleaner. When requirements change, you can update individual modules without rewriting the whole algorithm, preserving a stable overall structure. This is especially important in complex areas like finance and healthcare, where reliable collaboration and long-term maintainability are critical. Python code, modular algorithm design. This material focuses on modular algorithm design using simple temperature data processing as an example. It emphasizes breaking the task into separate functions so each step of the algorithm is clear and easy to understand. By organizing the work into distinct processing stages, it becomes simpler to see how data flows through the system. Finally, the program prints concise results that make the overall modular pipeline structure visible and easy to interpret. This line explains that no installation commands are needed because the script uses only Python's standard library. All the features it relies on are already included with a normal Python installation. As a result, you do not need any extra packages, which keeps the script simple. This also makes it easy to run in any standard Python environment without additional setup. This function loads a fixed set of raw temperature readings measured in Fahrenheit and returns them as a list of floating point values. The numbers are hard-coded to represent typical temperature measurements, allowing the function to simulate retrieving real data. Organizing the data loading in its own function keeps the code modular and makes it easier to change the data source later if needed. This function cleans a list of temperature readings by keeping only realistic values. It takes a list of readings as input and uses a filtering step to remove any temperatures outside the range of 50 to 120 degrees Fahrenheit. As a result, the function returns a cleaned list that contains only valid temperature values. This provides a more reliable dataset for any further analysis or processing. Is function converts a list of temperatures from Fahrenheit to Celsius. It takes each Fahrenheit value, subtracts 32, multiplies the result by 5, and then divides by 9. These operations apply the standard Fahrenheit to Celsius conversion formula. The function returns a new list that contains all the temperatures expressed in Celsius. This function summarizes a list of temperature readings by computing 3 key statistics. It finds the minimum value to show the lowest temperature and the maximum value to show the highest temperature. It then calculates the average by adding all the readings and dividing by how many there are. Finally, it returns the minimum, maximum, and average as a concise summary of the temperature data. The function starts by loading raw temperature readings in Fahrenheit, then cleans them by removing values outside a reasonable range. It converts the cleaned Fahrenheit readings to Celsius using the standard conversion formula. Next, it summarizes the Celsius data by computing the minimum, maximum, and average temperatures. Finally, it prints the original Fahrenheit readings, the clean Fahrenheit readings, and the Celsius readings rounded to 1 decimal place, along with the rounded minimum, maximum, and average Celsius values to give a clear overview of the process data. The program runs a temperature processing pipeline managed by a single coordinating function. It starts by loading raw temperature readings in Fahrenheit, then removes any values outside a reasonable range. The cleaned readings are converted to Celsius, and the code computes the minimum, maximum, and average of these Celsius values. Finally, it prints the raw, cleaned, and converted readings along with the summary statistics, making the structure of the algorithm clear and easy to follow. This script uses a modular approach to process temperature data. It starts with raw Fahrenheit readings, removes any values outside the realistic range of 50 to 120 degrees, and then converts the remaining values to Celsius using the standard formula. After conversion, it calculates the minimum, maximum, and average Celsius temperatures. When run, the script prints the original Fahrenheit list, the cleaned data, the Celsius values rounded to 1 decimal place, and the summary statistics, illustrating how each processing step is clear and reusable. Commenting and docstrings. Thoughtful comments and clear docstrings are essential for making algorithmic code understandable and reliable over time. The code itself often does not reveal the original intent, so comments should explain why particular choices were made. what assumptions they rely on, and how they relate to the overall problem. For example, they might note that a pruning step assumes non-negative travel times, or that a heuristic is tuned for urban traffic. Capturing these design decisions and domain insights in comments is crucial for anyone who needs to revisit or modify the algorithm later. Docstrings are important for clearly documenting the public interface of functions, classes, and modules. Unlike comments tied to specific lines of code, a docstring gives a concise overview of what an algorithm does, what inputs it expects, what outputs it produces, and any side effects or performance considerations. For example, it can state whether a ranking algorithm is deterministic, how it handles ties, and whether it is meant for real-time or batch use. This kind of documentation helps developers and tools understand how to use the algorithm safely without needing to study its internal implementation in detail. Comments and docstrings should be treated as part of the system design and kept accurate over time. If they become too detailed, outdated, or inconsistent with the current code, they can mislead readers. Focus on documenting the intent of the code and its key assumptions, and revise these notes whenever algorithms or behaviors change. This helps keep complex logic, such as processing steps in a detection system, easy to understand, review, and adapt as requirements evolve. Python code, commenting, and docstrings. This material focuses on writing helpful comments and docstrings for simple algorithmic Python functions. It emphasizes using comments to explain the intent behind the code, rather than restating behavior that is already obvious from the implementation. It also highlights the role of docstrings in clearly describing each function's inputs, outputs, and any important assumptions the algorithm relies on. Overall, the goal is to make code easier to understand and maintain by documenting purpose, usage, and constraints in a concise and meaningful way. This comment explains that the script does not require any pip install commands because it only uses features that come with Python by default. It tells the user that no external libraries are needed. As a result, anyone running the script can be confident that everything required is already available in a standard Python environment. This description explains a function that converts a distance from miles to feet. It takes one input, a miles value given as a floating point number, and uses a fixed conversion factor of 5,280 feet per mile. Inside the function, this factor is stored as a constant and multiplied by the input miles value to get the distance in feet. The result is then rounded to the nearest whole number, and the function returns this integer as the final distance in feet. Here we define a constant that stores the value 5,280, which is the number of feet in a mile. Using a constant makes the conversion factor clear and ensures it does not change anywhere in the program. We treat this value as a whole number, assuming we do not need to handle fractional feet, which keeps the calculations simple and easy to understand. This function converts a distance from miles to feet and returns the result as a whole number. It multiplies the miles value by 5,280, which is the number of feet in 1 mile. The result is then rounded to the nearest whole number and converted to an integer, so the final output is an integer number of feet. This function computes the total length of a route in feet from a list of segment distances given in miles. It assumes all distances should be non-negative and first checks the list for any negative values. If it finds a negative distance, it raises an error so that only valid forward travel distances are used. For the valid list, it converts each segment from miles to feet with a helper function, adds them together, and returns the total route length in feet. The code first checks whether any distance in the list of segments is negative, because the algorithm assumes all movement is forward and distances must be 0 or positive. If it finds a negative value, it raises a value error to indicate that the input is invalid and needs to be fixed. This safeguard ensures that the function only works with valid data and keeps the resulting calculations reliable. This code computes the total distance in feet for a list of route segments measured in miles. It does this by using a generator expression that goes through each segment, calls a conversion function to turn miles into feet, and produces the converted values one by one. These converted distances are then summed to get the overall distance in feet. This method combines conversion and addition in a single, concise, and efficient line of Python code. This function's final step is to return the total distance in feet, representing the complete route length. The accumulated distance has been computed within the function, and the return value makes this result available to the rest of the program. Other parts of the code can then use this total distance for additional processing or to display it to the user. This example function is created to show how documentation can be used effectively in Python. It defines a simple function called demonstrate_documentation that takes no inputs and returns nothing. Its main purpose is to display the docstrings and outputs of distance-related functions, illustrating how documentation is connected to what the code does. The clear docstring at the start explains this goal, making the function especially useful for teaching or sharing code with others. We define a list of floating point numbers that represent distances in miles for different segments of a route. These values, such as 1.2, 0.5, and 2.0 miles, model parts of a short city delivery path. This simple setup provides realistic test data for checking how our distance conversion and summation functions work. This code computes the total distance of a route in feet by processing several segments that are given in miles. A helper function converts each segment from miles to feet, and another function adds up all these converted values. The final total distance in feet is stored in a single variable. This result is then used to illustrate how the algorithm works and to support its documentation. We first print a short label to show that the next output is the documentation for the miles to feet function, so it is clear what the information refers to. Then, we access the function's documentation string through its special documentation attribute. This docstring briefly explains what the function does, what inputs it expects, and what it returns. By printing it, we show how built-in documentation can be displayed directly from the code to make the function easier to understand and use correctly. The code calculates and prints the total route distance in feet, and this result matches what the documentation says the function should do. By comparing the printed output with the documented description, you can see that the algorithm's behavior is consistent with its stated purpose. This alignment helps confirm that the implementation correctly fulfills its intended role. At the end of the script, a demonstration function is called when the code runs in an interactive environment. This function shows how the documented functions behave in practice by printing their descriptions and example outputs. By doing this, it links the written documentation to real results and clarifies the intended use and behavior of each function. This script shows how comments and docstrings document Python functions by using a simple distance example. One function converts miles to feet with a fixed conversion factor and rounds to the nearest whole foot. Another function adds up route segment distances in feet, allowing only non-negative values to represent forward travel. When run, the script prints the documentation for the miles to feet function and the total distance for a SAMPy route, illustrating how clear docstrings describe a function's purpose, inputs, outputs, and assumptions. In this lecture, you learn to refactor algorithm implementations to use idiomatic Python constructs without sacrificing clarity or performance, add effective tests and simple benchmarks to validate correctness and performance of algorithmic code, and evaluate and improve the readability and structure of Python algorithm implementations. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.